Our next topic is encoder. We are familiar with the words encode, decode in real life. For example, when we have a particular, say for example, in the case of cryptography or security issues, security topics, we have heard that when we send a particular item from one, sender or source to destination, we say that it should be encrypted, or we need to encode that particular uh, data so that it won't get what we call um, interfere with in the medium, interfere with the medium in between, so that others can recognize what is sent actually. So encrypting means actually what we do is we have a particular data, we convert it into a particular mode or into a particular fashion that others won't understand. Actually, in the case of encryption and decryption, what we do is we send this particular code, that is encode, in a particular format, and we send it to the destination, and the destination part they decode it, okay, or decrypt it. Okay, that is the case. If we have, say for example, if we have data, we encode it, that is make that particular data into a form that is not recognizable by any others, and we send it. And at the receiving end, what they do is they need to what encryption was done, we just perform the just opposite of that. Okay, so now we are going to discuss about the encoder concept. What is the concept behind encoding, and also in we also come across the concept of decoder. Okay, so what we do here in the case of encoder circuit or designing encoder circuit is, I have written a set of things that which will be helpful to you when you prepare notes. Okay, this is encoder, a device whose inputs are decimal digits and or alphabetic characters and whose outputs are the coded representation of those inputs. Okay, coded represent, the actual data is converted into a coded representation. That is, an encoder is a device which converts familiar numbers or symbols into a coded format. Okay, and an encoder has a number of input lines, only one of which is activated at a given time, and produces an n-bit output code depending on which input is activated. To get this concept clear, I will definitely say that we need to go for the design part. Okay, mainly we come across two designs, and for in that case we will get a basic idea regarding that. Okay, so this is the block diagram of the encoder. We have a set of m inputs starting from A0, A1, A2, etc. to AM minus 2, AM minus 1. M inputs, only one is high at a time, and from that we make the n bit output code, that is O1, O2, O3, etc. On minus 1, On minus 2. This is just the introductory part regarding encoder. Okay, we will next go into the different types of design based on the encoding concept. Okay. Okay. Next, our topic will be conversion of an octal or octal to binary encoder. Okay, we are familiar with the concept of octal number system. That is, we have values from 0 to 7 that are valid cases. Then that is 0 to 7 means 8 numbers. Okay, 0 to 7. Okay, here what I have done is octal to binary encoder means actually there are 8 numbers, right? That is 0 to 7 in the case of octal. Okay, to make 8 numbers, we can have a maximum of 2 raised to 3. That is 2 raised to 3 is 8. It's right? We have 2 raised to 3, 8. So an 8-bit octal number an octal number can be converted to maximum 3-bit code. Clear? So our construction we are going to construct an octal to binary encoder. So what we do is we have 8 octal numbers. So what we do is 0 to 7, that is 2 raised to 3 is 8. So maximum it can be converted from 8, it can be converted maximum to 3 binary. 3-bit binary, right? Okay, and the conversion part, D0 to D7. These are the possible combinations in the case of octal. So we write the corresponding by octal numbers also. The numbers 1, 0, 1, 2, 3, 4, 5, 6, 7. Okay, just 1 second. Yeah. Next is performing the basic operation here. Okay. Very familiar case. So there is nothing to learn in particular. Okay. As this is 0, this is 0, 0, 0. This is 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay. What we do next is, here actually we need to find values for A2, A1 and A0. Okay, very simple case. What we do is, A2 is equal to, see, this is 1 in this case, right? So we write this as D4 plus D5 plus D6 plus D7. Okay, next is A1, an expression for A1. How can we write this? D2 plus D3 plus D6 plus D7. Okay, next is A0. A0 can be written as D1 plus D3 plus D5 plus D7. Clear? Please go through. Okay. Okay, and finally the design. We had the truth table. We found the expressions for A2, A1, A0, and now we are going to draw the figure. Okay, when we draw the figure, yeah, D1, D2, D3, D4, D5, D6 and D7. Okay, some people may wonder why no D0. Okay, when we drew the truth table, when we constructed the truth table for encoder, that is octal to binary encoder, you might have recognized that, notice that in that particular case, when in the case of D0, A2, A1 and A0 values were 0, right? So D0 was not at all part of the game. So what we did is, we consider D0 as a don't care. Okay, so we can remove that D0. Next step is, just extend these lines. Okay, just extend these lines. I will always recommend the use of pencil. Okay, so that we can erase it properly. So we have D1 to D7. So A2 is A4, A4 plus, sorry, D4 plus D5 plus D6 plus D7. Second. Eight. Next one is A1. Okay, A1 means it's D2, sorry, D2 plus D3. Okay, D2 plus D3 plus D6 and D7. Next we have D1 D3 D5 and D7. This is easy. If you want, we can remove the extra lines. Okay, and this is the octal inputs and this is the binary outputs. Okay, please go. Our next topic is decimal to BCD encoder. Okay, decimal to BCD encoder. Here also the specialty is we are going to construct BCD. Okay, going to construct BCD. We represent this as 4 bits. Okay, actually 2 raised to 4 means we have 16. Okay, that is 0 to 50. Even though in BCD 10 cases are valid and the 6 are invalid, after constructing 2 raised to 3, that is 8, our next option is constructing 2 raised to 4, 16. Okay, we have 10 is a value in between. Hope you got the concept from this. Okay, 2 raised to 4 is 16, 2 raised to 3 is 8. We are going to construct a BCD encoder. Okay, we are going to construct decimal to BCD encoder. So what we do here is we have 10 valid states. So what the thing here is we need to go for the uppercase. Okay, that is 2 raised to 4. We should have 4 inputs. 4-bit case we are going to construct. Okay, 4-bit. Okay, here we have 10 cases, the valid 10 cases and the corresponding BCD outputs. Okay, and what about this case? We have 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. And this is similar to, the equivalent is clear. This is how we construct it. Okay, let me check. Yes, from this we need to get values for all these cases. That is A3 is equal to D8 plus D9. A2 is equal to D4 plus D5 plus D6 plus D7. A2. A1 is equal to D2 plus D3 plus D6 plus D7. A0 is equal to D1 plus D3 plus D5 plus D7 plus D9. Let me check the value, okay? 8, 9, 4, 5, 6, 7, 2, 3, 6, 7, 3, 5, 7, 9. Okay? Let's go through, okay? And this is the final design part. Earlier I have already shown how to draw the figure. This is another way of drawing, okay? In the previous figure what I did is all the inputs, just draw parallel lines, and from there we give the connection. If it's easy for you, please follow that. I used to follow such a method. It's an easy method, and this is another one in which you need to give some more concentration, okay? Otherwise it can get complicated. These are the values that we obtained earlier. A3 is equal to D8 plus D9. See, A3 is equal to D8 plus D9. D8 plus D9. A2 is equal to D4 plus D5 plus D6 plus D7. A2 is equal to D4 plus D5 plus D6 plus D7. And A1 is equal to, we have D2 plus D3 plus D6 plus D7. And A0 is equal to D1 plus D3 plus D5 plus D7 plus D9. Okay, this is also an easy method, but we need to have some concentration when we construct it, okay? Otherwise the full figure can get there can be mistakes, okay? The method I followed is the previous one. Go for parallel lines, and from there we give the connections, okay? This is how we construct this. And here also the D0 term is missing. The reason is that in the case of D0 the output was A0000, so it makes no what we call there we found in the truth table also, in the case of 0 we found 4 zeros, right? So there was no one value, so we can consider that also there was not actually any explicit input available. So what we do is we just ignore it, or we can consider D0 as a don't care condition. It's actually, in the case of BCD we can't say that it's don't care, because all the rest of the values in figures to come we will understand that the invalid conditions are considered as don't cares in the case of BCD. But for the time being, what you need to understand is D0 had no explicit input case, so what we do is we just ignore it, because the output we obtained was corresponding to 0, we had 0, 0, 0, 0, there was no one value, so D0 was not so useful in this particular case. So what we do is we construct the figure from D1, D2, D3 till D9, okay? And the thing to remember, rest of the topics I will explain in the topics to come, and about the BCD construction node, okay? So for the time being, the decimal to BCD encoder, follow this figure, or you can draw the other way. So but focus on the way you construct the picture, okay, or the diagram, okay?